Welcome to The Explainer. Today, we're diving into the incredible 80-year journey of artificial neural networks. We're going to trace how a really simple idea, inspired by the human brain, evolved into the powerhouse AI that is, well, completely reshaping our world. It all really started with this one question. I mean, it sounds almost impossibly ambitious, right? But this single, powerful query has been the engine driving decades of research, innovation, and some major breakthroughs. And it all started with the surprisingly simple, yet absolutely revolutionary concept. To really get a grasp on the AI of today, we have to look back at where it came from. See, this wasn't a single invention, but a story that kind of unfolds in three distinct acts, three eras of development that each solved a critical piece of the puzzle. So our journey kicks off back in the 1940s with the very first spark of an idea. Then it moves through the mid-century, which is where we figured out how to actually make these models learn. And that all brings us to today, where we're taking a deep dive into handling the complexity and, the uncertainty of the real world. Okay, let's get into it. So before you can even think about building an artificial brain, you have to build one single artificial brain cell. The very first challenge was a fundamental one. How do you take something biological, a neuron, and capture its essence using the language of math? The answer came in 1943 from McCullik and Pitts. They published what they called a logical calculus, which was basically the first ever mathematical model of a neuron. It was this radical idea that boiled a neuron's job down to its absolute basics. It takes in signals and produces a simple binary output. You can think of it like an on or off switch. And how it works is just beautifully simple. Here's the deal. The neuron gathers up all the signals coming into it and adds them together. Then it just checks if that total sum is strong enough to cross a preset limit, a threshold. If it is, boom, it fires an on signal. If not, it just stays off. That's it, a simple decision maker and the very first building block of the artificial brain. But okay, a network of on-off switches, no matter how many you've got, can't really be called intelligent if it can't adapt. So the next great leap was figuring out how to make these networks learn from experience, just like we do. And this is where the real intelligence starts to kick in. This marks a huge shift in thinking. We moved away from trying to handcraft these fixed, rule-based systems and started creating adaptive, data-driven networks. So instead of programming in all the rules, the goal became letting the network figure out the rules for itself, just by looking at a ton of examples. And this era gave us the foundational tools for learning. The most critical one was this idea called gradient descent. Okay, think of it like this. You're a hiker trying to find the bottom of a valley, but it's totally foggy. You can't see the bottom, but you can feel which way is downhill, right? So you take a small step in that direction, check again, and repeat. Gradient descent lets the network do the exact same thing with its mistakes. It feels which adjustments will make it less wrong, and it takes teeny little steps over and over until it gets really good at whatever it's doing. This one core idea powers most of the learning in AI today. But here's the next big hurdle. The real world isn't a neat collection of on or off, yes or no problems. It's filled with shades of gray. It's messy, there's missing information, it's ambiguous. And this posed a massive challenge for an AI that was built on pure binary logic. And that quote it nails it. For AI to become truly useful in things like medicine or finance, or even just understanding human language, it had to stop thinking only in certainties. It needed to learn how to reason with probabilities and operate confidently even when the answer isn't 100% clear. Now, solving this didn't just mean tweaking the old algorithms. It required a revolutionary leap forward. It meant creating entirely new mathematical frameworks, ones designed specifically to give deep learning models the ability to navigate and even quantify uncertainty. A key innovation here is a concept called neural expectation operators, or NEOs for short. Okay, this gets a little technical, but the core idea is pretty brilliant. NEOs basically use neural networks to model the ambiguity itself. It's a way for the AI to represent and reason about a whole range of possible outcomes, not just a single definite one. So here's the crucial point. This new math wasn't just some abstract theory. It had massive practical payoffs. It built a bridge between theory and what people were actually doing in machine learning. It removed old mathematical roadblocks, and it made these advanced ideas compatible with the fast, efficient network designs we use today. And even better, it gave engineers a way to build desirable properties like reliability and predictability directly into the AI's architecture. It made them more trustworthy by design. So after this incredible 80-year journey, from a single switch to learning networks to AI that can actually reason about ambiguity, what's the payoff? I mean, what can these incredibly sophisticated systems actually do? Well, this brings us right to the cutting edge. Today, these concepts are powering fields like reinforcement learning, where an AI teaches itself to master a video game or navigate a robot just by trial and error. And in a totally different area, transformer models, yep, the same kind of architecture behind tools like ChatGPT, are now being used as creative partners for human mathematicians, helping them find new ways to solve incredibly complex proofs. This decades-long quest to build an artificial brain has taken us from a simple sketch of a neuron all the way to machines that can partner with us in scientific discovery. It's brought us right here, to this moment, leaving us with what is, maybe, the most exciting and profound question of all.